Welcome back, everyone, to another deep dive into the world of mathematics. I'm so excited to, dive into this fascinating research paper.
Yeah, this one should be pretty interesting.
So it's all about trying to predict how much clamping force a bolt has. When you tighten it down, how much force is actually holding those parts together, the preload. And it's way more complicated than you'd think.
Oh, yeah.
This paper combines like a theoretical model with some really cool data analysis to try and make those predictions as accurate as possible.
That's the goal, right? To go beyond just guessing and tightening and get those bolts just right.
Exactly. It's all about precision, especially when you think about, where bolts are used. We're talking bridges, airplanes, even just your car.
Critical stuff. So where do we start?
Let's start with the basics. What's actually going on when you tighten a bolt? Our Wikipedia source on bolted joint, it describes a preloaded tension joint.
Right, so you're essentially stretching the bolt when you tighten it. That creates tension, and that tension translates into a clamping force between the parts you're joining.
Okay, so the preload is like the constant squeezing force that's holding everything together.
That's it. And that's why it's so important, especially when you're thinking about things like preventing the joint from coming apart or, failing under stress, which happens more than you'd think.
So applying torque to the bolt creates that preload. But the paper suggests that it's not as simple as tighter bolt equals more force.
Yeah, you can't just assume that. There are all sorts of factors that can throw things off. The geometry of the threads, the friction between the threads as you're tightening, the friction under the bolt head, even just the materials themselves can play a huge role.
So it's almost like trying to solve an equation with a bunch of missing variables.
It kind of is. And that uncertainty gets reflected in something called the torque coefficient. It's supposed to help you predict how much torque you need for a certain preload, but it can change dramatically in real-world situations.
And then there's the net factor, which we found in that Wikipedia article, which adds another layer of complexity. So with all this uncertainty, how does this research try to tackle the problem?
Well, they've combined a couple of approaches. They start with something they call a mechanism model, which is basically a mathematical description of what's happening when you tighten a bolt.
So they're trying to build a model of that ideal scenario, like a perfect world where everything behaves exactly as you'd expect.
That's a good way to put it. And they take it even further, accounting for things like friction, both in the threads and under the bolt head. They actually visualize this in Figure 1 and even have an equation for it, Equation 8.
Sounds pretty comprehensive.
Yeah.
Did they test this model out?
Oh, yeah, they did. They used a bunch of different bolt sizes, which you can see in Table 1. And while the model was a decent starting point, its predictions didn't perfectly match what happened in their experiments.
Well, with so many variables at play, I'm not surprised.
Right, especially friction. Predicting friction accurately in the real world, that's tough. So that's where they bring in the data.
Okay, so they're taking the theoretical model and refining it with real-world observations.
Exactly. They use something called parameter sensitivity analysis to see which variables have the biggest impact on the final preload.
So it's like they're zeroing in on the most important pieces of the puzzle. How do they actually do that?
They basically tweak each parameter one by one and see how much it changes the preload. They even have some great visuals of this process in Figures 9 and 10. Through that process, they were able to pinpoint the most influential ones, like the friction coefficients for the threads, and under the bolt head, the diameter of the bolt, and of course the torque itself.
So they found the key players in this game of bolt tightening. Now what?
Well, they took all that newfound knowledge, along with data they collected using a special fastener tightening machine, and used it to create an even more refined model.
Ooh, so they're really bringing in the big data guns now.
They're using something called Gaussian process regression, or GPR, to take all those variables and predict both the average preload and a range of likely values.
I see. So instead of just giving one answer, it's like, here's the most likely outcome, but it could also be a little higher or a little lower.
That's the idea. And our source material even mentions kriging, which is a statistical tool that GPR is actually built upon. It's all about making predictions with limited data, which is pretty cool.
So they're combining this fancy statistical modeling with real-world data to try to get the most accurate predictions. What were the results? Did it work?
The results were impressive. They got an accuracy of over 98.18% under various conditions. You can see the breakdown in Table 6. It really shows the power of this combined approach.
Wow, that's amazing. So they were able to significantly improve the accuracy of their predictions.
Exactly. And they didn't stop there. They actually developed software based on this model to help engineers use it in practice.
So they're taking this from a research paper and making it a real-world tool.
Precisely. And that's what's so exciting about this research. It's a great example of how we can use math and data analysis to solve real-world problems.
Absolutely. Okay, so before we move on, let's quickly recap what we've learned so far. What's the main takeaway here?
I think the biggest takeaway is that accurately predicting bolt preload, just based on how much you tighten it, is way more complex than it seems. There are a lot of factors that can mess things up.
Like all those variables we talked about, especially friction.
But this research shows that we can improve those predictions dramatically by combining a physics-based model with data analysis.
And that level of accuracy is super important
Because
because
bolted connections are everywhere. Think about it. Bridges, buildings, airplanes, cars, they all rely on bolts to stay together. Having a reliable way to predict how strong those connections are is crucial for safety.
so it's not just about tightening a bolt. It's about understanding all the forces involved and making sure those connections can handle the stress they'll face.
Exactly. And that's why this research is so important. It's about making our world safer and more reliable.
Now, here's a question for you, our listener. How do you think this research might impact other industries? Not just the obvious ones like construction or aerospace.
It's a great question. There are so many areas where reliable fastening is critical, from medical devices to electronics to, well, you name it.
It's really mind-blowing to think about the potential applications.
It all starts with understanding the basic principles, even in something as seemingly simple as a bolted connection. There's a whole world of math and engineering underneath it all.
We encourage you to check out the sources we've linked, especially the research paper itself. It's a fascinating read. But before you do that, stay tuned for part 2 of this deep dive, where we'll explore some even more advanced concepts from the research.
You know, what's really cool about this whole sensitivity analysis thing, it's not just about getting the prediction right, it's about understanding why things are uncertain in the first place.
Oh, I see what you mean. It's like they're giving us a map of all the potential problems that could crop up.
Yeah, exactly. By identifying those key parameters, the ones that really matter, engineers can focus on getting those right. It's about making informed decisions, not just blindly tightening bolts and hoping for the best.
So it's a more analytical approach, moving away from just trial and error.
Right. And that's especially important nowadays where everything has to be so precise and reliable, especially in things like aerospace or, high-performance cars.
You mentioned earlier that they actually created software based on this model. Can you tell us a bit more about that?
Oh, yeah. That's a huge part of making this research useful for engineers out in the field. I mean, not everyone's going to be digging into the nitty-gritty math of GPR, right?
No, it's like they're taking all that complex stuff and making it accessible.
Exactly. They've built this software where engineers can just input the specific details of their bolted joint, the bolt size, the materials, the friction coefficients, all that stuff.
And then the software uses the model to predict the preload.
Yep. And it doesn't just give you a single number. It gives you a range of possible values, that confidence interval we talked about, so you can see how much variation you might expect.
So it's like having a smart assistant that tells you, okay, this is the most likely outcome, but be aware that it could be a bit higher or lower.
That's a great way to put it. It gives engineers more information to work with, which is always a good thing. They might decide to use a different lubricant or change their tightening technique based on that.
So it's about anticipating potential problems before they even happen.
Exactly. It's a much more proactive approach to engineering. And it all comes back to using math and data analysis to solve real-world problems.
This whole paper really shows the power of those tools.
No doubt. It's about bringing a level of predictability and precision to something that can often feel pretty uncertain.
But even with these powerful models, aren't there still some assumptions baked in? I mean, there are limitations to any model, right?
Oh, absolutely. It's important to remember that. For example, that mechanism model we talked about earlier, it uses a simplified representation of a bolted joint.
So it might not perfectly reflect every real-world scenario?
Exactly. And that's where the data-driven part of the GPR model really shines. It helps fill in those gaps and refine those predictions. But even GPR relies on statistical assumptions.
So it's not a foolproof solution, but it's a powerful tool.
Exactly. It's about using it intelligently in conjunction with good engineering judgment and experience. You can't just blindly trust any model. You have to understand its limitations.
This whole deep dive has been really eye-opening. I never realized how much complexity there is in something as simple as tightening a bolt.
It's one of those things that you don't really think about until you start digging into it. And then you realize there's a whole world of math and engineering behind it.
And that math can really help us create more reliable and robust solutions.
Definitely. It's about understanding the forces at play and controlling them to achieve the outcome we want.
Now, we've been focusing on a specific type of bolt, but I imagine these principles could be applied to all sorts of fastening systems.
Oh, absolutely. The fundamental ideas are the same. Understanding the physics, gathering data, and using that data to refine our predictions.
So this could lead to better designs and safer products in all sorts of industries.
Think about it. More robust cars, safer airplanes, stronger buildings. The potential impact is huge.
It's all about pushing the boundaries of engineering and building a better, safer world.
And it all starts with understanding the basics, even in something as simple as a bolted joint. There's always something new to learn.
This deep dive has been a fascinating journey into the world of mechanics, statistics, data science. It's all connected.
It really highlights the power of human ingenuity, this constant desire to understand the world around us and make it better.
And that's what makes exploring these topics so exciting. We get to uncover the hidden depths of things we take for granted and see the amazing math that's working behind the scenes.
Speaking of uncovering hidden depths, we've talked a lot about the importance of data, but what about the quality of that data? I mean, if you're feeding bad data into a model, you're going to get bad results, right?
That's a great point. Garbage in, garbage out, as they say. So how can engineers make sure they're using good quality data for this kind of analysis?
That's the key question. It all comes down to careful planning, meticulous data collection, and making sure you're validating your data every step of the way.
It's about treating data with the same level of rigor as any other engineering parameter.
Exactly. Data isn't just something you collect and throw into a model. It's a valuable resource that needs to be managed carefully.
And that brings us back to the importance of mathematics.
Right. It gives us the tools to understand and interpret that data to make sense of it all.
And with that, dear listener, we leave you with a challenge. The next time you see a bolted connection, take a moment to think about all the forces at play.
Think about the math and data that are working behind the scenes to keep that connection strong.
And if you're feeling adventurous, dive into those sources we provided and explore the world of bolt preload prediction for yourself.
You might be surprised by what you discover.
Join us for part 3, where we'll wrap up our deep dive into this fascinating world. And we're back for the final part of our deep dive into predicting bolt preload. We've been talking about all sorts of cool stuff like physics models and data analysis, but there's one thing I'd love to unpack a little more. That Gaussian process regression, the GPR. It sounds pretty intense.
Oh, it can seem that way, for sure. But the basic idea behind it is actually pretty straightforward. It's all about how we deal with uncertainty. You see, instead of trying to find one perfect formula to predict the preload from the torque, GPR considers a whole bunch of possible formulas.
So it's not like this is the one right answer. It's more like, hey, here's a whole range of possibilities, and some are more likely than others.
Exactly. And it even assigns probabilities to those possibilities. It's like, we're 70% sure the relationship is like this, but there's a 20% chance it's more like that, and so on.
Okay, so instead of one single curve on a graph, it's more like a whole cloud of possibilities.
That's a great way to visualize it. And that cloud is shaped by something called a Gaussian process, which is where the name comes from.
Gotcha. So how does GPR actually use this cloud of possibilities to make predictions about the preload?
It uses something called Bayesian inference, which is a fancy way of saying it starts with an educated guess, and then it refines that guess based on the data it sees.
So it's like, we think it might be like this, but let's see what the actual measurements tell us.
Exactly. And as it gets more data, that guess becomes more and more refined. It's a constant process of learning and improvement.
And the cool thing is those predictions aren't just single numbers, they come with confidence intervals.
Right. Right. It's not just saying this is the preload. It's saying we're 95% sure the preload is somewhere between this value and that value.
It's like acknowledging that there's always some uncertainty, some wiggle room. which makes sense, given all the variables involved.
Exactly. And that's what makes GKR so powerful. It doesn't pretend to have all the answers. It gives you a range of possibilities and tells you how confident it is in those possibilities.
It's a really elegant way of dealing with a complex problem. This whole deep dive has been a great example of how different areas of math can come together to solve real-world problems. We've seen mechanics, statistics, data science, they're all intertwined.
Yeah, it's not just about knowing one type of math. It's about seeing how they all connect and work together. And that's where the real power lies.
As we generate more and more data and our computational tools get even more sophisticated, I think this kind of interdisciplinary approach is going to become even more important.
Oh, absolutely. The future of engineering, and really any field that deals with complex systems, is going to rely heavily on this kind of thinking.
It's exciting to think about all the potential applications, from designing safer structures to developing groundbreaking new technologies.
It all comes back to using math to make a positive impact on the world. And that's what makes it so rewarding.
It's been a real pleasure exploring this topic with you today. We hope our listeners have enjoyed this deep dive into the fascinating world of bolt preload prediction.
Absolutely. We've only just scratched the surface, but hopefully we've sparked some curiosity and inspired some folks to dig a little deeper on their own.
We always encourage our listeners to check out the sources we've linked, especially the research paper itself. There's a wealth of information there for those who want to delve further.
And who knows, maybe some of you listening will be the ones to make the next big breakthrough in this field.
That's the beauty of knowledge. It's always evolving, always expanding, and we're all part of that journey.
Well said. And on that note, we'd like to thank you all for joining us on this mathematical adventure. We'll be back soon with another deep dive into a fascinating topic. Until then, stay curious and keep exploring.